So we define this hierarchy of properties, but we have not shown there a strict hierarchy except showing that T1 does not mean Hausdorff, where we had a natural enough example of cofinite topology, and I mentioned there are many others. Regular but not normal we'll see as an application of bare category theorem. So it's quite non-trivial, and also before that we'll see that under certain additional hypothesis regular does imply normal, which is nice because we then only have to verify regularity to use the Tietze extension theorem or the Urison lemma. But how about Hausdorff but not regular? We'll quickly sketch an example of this. So X is going to be R, but open sets. So I'm going to call it X, not R, just to avoid confusion as to what you're calling an open set. Where open sets are U minus C, where U open in R. R is R with the usual topology. So the sets are the same, but the topology is different. And C is countable. Okay, why is this a topology? It's topology for the same reason as cofinite. We can always in fact define the co-countable topology. Basically the finite union of countable sets is countable, and the finite intersection, well rather if I take an arbitrary intersection of countable sets, it's contained in one of them, so it's also countable unless it's an empty intersection. So the same argument tells you this is a topology, and the claim is, so this is Hausdorff. Well, why is that? Because the R is Hausdorff. So there is no problem. And so this is finer than R. So if you have 2 points which are finer than R, so remark, if a topology is Hausdorff, so is a finer topology. Mentioning this because it's a nice thing to know that you refine a topology, it remains Hausdorff. Because if given open sets containing these, they are still open in the finer topology. Your C is empty is an example of a countable set. Countable doesn't mean it's countable in infinite. It could be. Yeah, so it's a finer topology. Yeah, so it's a finer topology. So but what about regular? The same argument doesn't hold, because regular says for all closed sets, and the finer topology has additional closed sets, namely all countable sets in this particular case. So regular is not inherited either way when you get coarser or finer. So it's not regular. Here we need a closed set and a point. Take P equals just the point 0, and take the closed set here as the set of all 1 over n, where n is greater than or equal to 1. So natural numbers. So it's a sequence that converges to P in a sense. This would not be closed in the Euclidean topology, and so you could not do this in the Euclidean topology. It would contain this as a limit point, but C is countable, so closed as it is countable, and we cannot separate. Okay, so cannot separate. Okay, namely given, I'll call them U1 minus C1 and U2 minus C2. These are the countable sets such that P is in U1 minus C1 and C is contained in U2 minus C2. Well, we claim they intersect. Minus C1 intersection U2 minus C2 is not empty. So having an empty intersection is what was separation. So here's the line. We have the line here, and then we have the point 0, and then we have a whole bunch of points that approach it. Okay, and let's just draw a picture. So U1 contains a ball. Okay, so U1 contains a ball, and that contains some point of the form 1 over n for n large enough. Okay, and now if I have a neighborhood which includes 1 over n, the U2, so U2 should include a neighborhood of 1 over n, this region. Okay, so namely, so this is just saying that because we are simply using the basic properties. So in fact, I can just say as 1 over n converges to 0. Okay, u1 intersection u2 is non-empty. Okay, in fact. So these are two open sets which are non-empty. Okay, in fact. Let me be specific. So u1 contains ball around 0 of some delta, or some delta greater than 0. Okay, and there exists n in n natural number such that 1 over n belongs to the ball of radius delta around 0. I changed my notation a little bit. This is another standard notation for a ball. Okay, so now we have 1 over n belongs to this ball. Okay, and therefore it follows, so there exists some delta prime such that, now let me switch back to the usual notation, ball around 1 over n of radius delta prime is contained in the set u2. Okay, what follows from this? Hence, u1 intersection u2, the intersection of two balls, is uncountable because it contains in fact an entire segment in the line. But c1 and c2 are countable. Therefore, u1 minus c1 intersection u2 minus c2 is non-empty. Okay, so modified co-countable topology, sort of relatively co-countable topology, gives us an example of things that are housed off, but they are not regular. Okay. So this will end our set on separability till, well, we'll come back to it because we'll come back and show separabilities. We can upgrade from regular to normal under the next set of conditions, which are telling you how big a topology is in terms of cardinality.